A polynomial can be thought of as simply a special kind of mathematical expression. These are all polynomials. This is a polynomial in x, this is a polynomial in x, this is a polynomial in x and y. The peculiar thing about polynomials is the structure of each term. Each term has the structure ax to the k power, where a is any real number and k is either 0 or a positive integer exponent. Now the x is just standing in for a variable, and it could be 2 letters here as we see in this polynomial. But at any rate, it's this kind of structure for each of the terms. Now the degree of a term corresponds with the exponent on a variable. That is, here this is a first degree term, this is a second degree term, this is a first degree term because of the understood 1. The degree of this term is the sum of the 2 exponents. It would be a fourth degree term. The degree of this term is 1 and 1, 2. Now we could think of the constants as having degree 0 because after all we could think of something like x to the 0 power here being associated with that term. Now, the polynomial has degree as well. This is a second degree polynomial because the term of highest degree is 2. This is the term of highest degree, and it's a second degree term, so it's a second degree polynomial. Coefficient refers to the number part in a term. The coefficient in this term is 5, the coefficient here 3, the coefficient here -4, the coefficient here 5, the coefficient here is 2. Now, there is a standard form for writing polynomials. We generally write the term of highest degree first, and then the next degree term, and so on down to the constant term. These are all in standard form. Now, when polynomials are in standard form like this, the leading coefficient, or the first coefficient that we see, will be the coefficient of the highest degree term, and it's often called the leading coefficient. So the leading coefficient here is 3, the leading coefficient here 2, the leading coefficient here 5. There are certain categories for polynomials according to the number of terms that they have. A polynomial with 1 term is called a monomial. If it has 2 terms, it's a binomial, and 3 terms, a trinomial. Other than that, they are simply generally polynomials. And in fact, monomials, binomials, and trinomials are also just polynomials as well. Suppose we want to write this polynomial in standard form. We would write the term of highest degree first. We would look through and see that this is the largest exponent on a variable. And so we would write the -5 x to the 7th as the leading term, and then the term of next degree, let's see, that would be this one, and then the 3x, and then the constant -2. So this is a 7th degree polynomial, and the leading coefficient is -5. We're going to go through a number of operations on polynomials now. Once again, this is just a review, I'm sure, but we're going to talk about adding, subtracting, multiplying, and dividing polynomials right quick. To add polynomials, or to add the terms within a polynomial, we're just looking at like terms, and like terms are terms that have the same letters, and those letters have the same exponents on them, and to bring them together, we just bring together coefficients. So here we have a couple of like terms. We're adding these 2 monomials, you see, and we identified them as like terms because they both involve x and y. The x is squared in both of them, and y is to the first degree. Now, to bring them together, we have -3 of these things plus 5 of those things. -3 plus 5 is 2, so we have 2x squared y for the collection of them. Here we're subtracting a couple of polynomials. This is a trinomial. We're subtracting that trinomial. In order to complete the calculation, we need to burn a step here. We always need to write another step that allows us to drop the parentheses. It's really important to do that, especially when you're subtracting, because the subtraction here says that we're changing all of these signs in order to collect with the terms over here. And we can think of it as minus understood 1 times every one of these terms in order to complete that sign change operation. So all I've done is drop the parentheses here and bring these down because the understood coefficient here is 1. That's one way to look at it. And here, minus 1 times all of these, the signs change. This becomes minus 3x to the 4th plus 4x squared minus 3x. And now I want to collect like terms. Now you look around for like terms, and you could reassociate in the problem to put the terms of the same degree next to one another if you want to, but really day to day we're probably not going to do that. When you identify like terms, though, I think it's helpful to do this, is just underline a couple of terms that are alike. That calls your attention to them right quick. 7 of these things minus 3, that would leave 4x to the 4th, and you write that down. And now you're finished with those. You could X them out if you want to, or you could go to the next term, or the next group of like terms, and that would be, let's see, the x squared terms are alike. I'll put a different kind of underline under them. And I have minus 1 of these, plus 4 of those. Together we have plus 3x squared. Now we look for any other group of like terms. Well, I don't see another constant term other than this one, and I don't see another first degree term other than this one. So we just bring those terms down. We bring down the minus 3x, bring down the constant, and we're done. To multiply polynomials, the concept is that we are taking every term in one polynomial and multiplying times every term in the other polynomial. And if you just understand that idea, then there are many, many different methods that will work just fine. You probably learned the FOIL method at some point in time earlier. The FOIL method, the idea of first, outer, inner, last. First means first times first. Outer means the outer 2 terms. The inner 2 terms for the I and the L means the last 2 terms. So that accomplishes what we're after here in multiplying every term here times every term over there. I kind of like to do this. Just pick on one term here and multiply times every one of those. And then pick on the next one and multiply times every one of those. And then if you have a trinomial times a trinomial, you use that strategy and it comes out just great. At any rate, it looks like this. 3x times 5x, 15x squared. Then 3x times 7, 21x. Then this term times each of those. Minus 2 times 5x, minus 10x. And then minus 2 times 7, minus 14. And now it's often the case when you multiply a couple of binomials that you have some collection. Those 2 terms are alike. We bring down this 15x squared, collect 21x minus 10x, we have 11x, and then bring down minus 14, and this is our answer. Another arrangement of the 2 binomials for multiplication is a vertical arrangement. We don't often use this, but I just want to make you aware that it's possible. We could arrange them vertically like this and multiply, let's see, 7 times negative 2, that's negative 14, and then 7 times 3x is 21x. Then 5x times negative 2 is minus 10x. Now notice how I'm putting the minus 10x under the 5x, and it also accomplishes the idea of having these terms of the same degree kind of line up for collection a little bit later. Then 5x times 3x is 15x squared. Then I draw the line and collect. This is very similar to the idea of multiplication in arithmetic, and this idea of readjusting the digits, you see, allows us to have digits of the same value added in various columns. So we're accomplishing the same idea here. At any rate, 15x squared, then collecting these 2, we get our 11x, and then minus 14 for the final answer. Recall that when we multiply the sum of 2 terms times the difference of the same 2 terms, the middle term sort of goes out and we get the difference of squares. Here's the long version of that. X times x is x squared, then x times 5, 5x, and minus 5 times x, minus 5x, then minus 5 times 5 is minus 25. And we end up with x squared, and these terms go out, then minus 25. And the fast way to do this is that when we see the sum times the difference of the same 2 terms, we can just say we get the difference of 2 squares. So it's the first term squared minus the second term squared. You see, and that's all there is to it. So when we bump into a problem like this, we recognize it as sum times difference of the same 2 terms, and we can think more in this way than the other way. You see, it's the first term squared minus the second term squared, and evaluate it sort of like this. So we have 49x squared minus 16. Here we're squaring, and notice we have the sum of 2 terms squared. Now, it turns out that sum and difference behave in pretty much the same way. But we want to examine the fast way of squaring a binomial here. Now, I'm taking the long route right here. We have two factors of x plus 3, and we use the FOIL method to multiply. But notice that these two terms are exactly the same. So we have two of those things here, and I'm emphasizing it here with this step. And this thing that we have two of is nothing more than the product of those two. So the middle term turns out to be double the product of these two. And the first term is the first term squared, the last term is the last term squared. The middle term is just double the product of the two. Now we can use that idea to deal with a problem like this. Now we're squaring a binomial, so we recall this kind of pattern, and it's a pattern where we think, well, the first term is going to be squared. The next term is double the product of those two. So it's 2 times 4x times 7. And then the last term is the last term squared, and that's all there is to it. And then we perform the indicated operations to get it all of the terms. Squaring here, we get 16x squared. And then let's see, 2 times 4, 8 times 7, 56. X, and then 7 squared, 49. And when we have the difference of two terms, all squared, it's the same idea. It is that, let's see, we're squaring, so the first term of our answer is going to be this first term, all squared. The middle term is going to be just double the product of these two, so it's double 5x times negative 9. And then the last term is the last term squared. Now, it doesn't matter whether we put a plus or a minus in here. For with the 9, when we square, we're going to get a positive result. So let's see, we're squaring here, we get 25x squared. Then the middle term is going to be negative, because one of these factors is negative. And then 2 times 5, 10 times 9, 90x. And then 9 squared, 81. Take a look at this pattern. Here we're cubing a binomial. Now, I'm going to use A and B here rather than a number and a letter, because we just want to notice a pattern here. A plus B cubed means we have 3 factors of A plus B, so I can list them like this, and then I can just expand as we normally would. Using the FOIL method on these two, I get this, A squared plus 2AB plus B squared. Using the FAST method, you see it would be the first term squared plus double the product of the two, and then plus the last term squared. Okay. Now, I'm just multiplying each of these two terms times every term over here. So A times all of that would be these 3 terms. B times all of that last 3 terms. Let's bring together the like terms. We only have one A cubed term. Then we have a term that is A squared B. You see this contains A squared B. This one contains A squared B. Collecting coefficients, 2 plus understood 1 would give us 3 of these A squared B terms. And then in a similar way, we only have one term of AB squared, or excuse me, we have one AB squared here. We have 2 AB squared here. So together we have 3 AB squared. And then we bring down the B cubed. Now here's the pattern we want to recognize. Think about A and B as just items that fill positions within our original problem. So this is nothing more than the first entry up there cubed. This is 3 times the first entry squared times the second entry to the first degree. This is 3 times the first entry up there in the binomial times the second entry squared. And this is the second entry cubed. If we recognize this pattern, if we use this pattern, then we can very quickly deal with something like, oh, let's say, x plus 5 cubed. Let's go with the pattern now. It's the first entry cubed. Then there is a sort of a naturally occurring coefficient 3. And then there is the first entry squared as an additional factor. And then another factor is one factor of this second entry. So we have a 5 here. And then we have the naturally occurring coefficient 3, and then A, the first entry, that's x in this case, and then the second entry is squared. You see, that's the idea. That's the replacement idea. Sometimes you can do this mentally very, very quickly once you become accustomed to it. And then the last term is the second entry cubed. So now we'll go through and evaluate just a little bit. We have x cubed. And then we have 5 times 3, that's 15x squared. And then 25 times 3, 75x. And then 125 as the final answer. Let's go through it again. Let's complicate things a little bit more. We have 3x minus 2 all cubed. So with this idea, let's see, the first term is going to be the first term here cubed. The second term has sort of a natural coefficient 3, and then we have the first term squared and the second term to the first degree. Now notice the appearance here of this negative sign. That's okay, it'll just jam in here with these factors and we'll end up with a condition of alternating sign, but it's really no big deal. All right, then in the next one we have this naturally occurring 3, and then we have 3x, the first term, to the first degree, and then our second term squared. And then our last term is the second term cubed. All right, let's go back through and evaluate a bit. Cubing here, we're cubing 3 to get 27, and then x is cubed. Now let's see, can we do all of these at one time? Maybe we can. We're squaring the 3 to give 9. 9 times 3 is 27, times minus 2. That's minus 54 x squared. And then in this one, let's see, we're squaring the negative 2. That gives 4. 4 times 3, 12, times 3, 36. So we have 36x. And then here we're cubing the negative 2, and that's minus 8. Now, notice the alternating sign pattern, plus, minus, when we have a difference that's being cubed.